All right. So, welcome to another life science session. Today, we have a bit of a, at least from my side, a bit of a different bit of content. We are going to be exploring something that came up last week. Some of our viewers might remember that Nick and I stumbled upon a seeming coincidence or a pattern that was kind of serendipitous, and we wanted to just give us the space and share with all of you this kind of thought process. So maybe Nick can refine my explanation in a moment, but I'm going to try and frame what the kind of seeming coincidence here is. So basically, we were looking at some of Nick's wonderful visualizations of quantum geometry, the kind of the tetrahedra that represents probability spaces and all these kinds of things. And, I noticed that a very specific 3D object that I had encountered for completely different reasons. And so today, we I think the goal should be that we try and discern and understand a little bit where this is coming from. So probably it would be a bit of Nick presenting this is the thing, me presenting this is the thing, and then I have some open questions. This can always be left as exercise for the community. If you guys answer those questions, actually you have publications ready to go, so you can go ahead and have your own papers in pure algebra if you answer them. I don't think they're very difficult questions, but they are questions that I'm very unfamiliar with, and so I have little power to actually answer. But anyway, I think that's the plan. I think that's how I understand it. The 3D structure is very concrete. We will draw it. Nick will show some graphics. It's very simple. And it seems to have this very serendipitous, as I say, intersection between some quantum geometry and something to do with, as I'll explain, higher rarity commutators. So we'll see if this goes anywhere. So Nick, do you want to start us off with some context from the
Well,
quantum
I
geometry?
can show whatever I was shown last time.
Yeah. Yes.
Uh,
Bring us up to speed.
It's like this is the object you're talking about, right?
It is.
So this is in the context of the quantum computation, this is like the familiar block sphere, right? Those tetrahedron are the phase space bases that you can cast your quantum state into and think of them as a quantum probabilities, right? But there is a natural duality between those bases, which is also geometrically just corresponding to two dual tetrahedron, right? All those vertices correspond to the triples triality of free projective axis and the block sphere and all that, right? I don't know. So what do you want to do with these covers? Because I have no idea. what plans do you have?
So I think okay. So there's one part. Okay. So let me now share and explain where this comes from. Let's see. I think that should be fine. Okay. Right. So the quickest way to introduce this is if one is thinking about ternary operations and how one generalizes how one generalizes notions from binary operations to ternary operations. A very basic notion in binary operations is the commutator, right? So the first kind of non-trivial, non-commutative operation that one studies in mathematics is matrix multiplication. One writes A times B for matrices, and then the order matters. And so because the order matters, you might want to symmetrize this product. And so you might want to do something like A times B symmetrize, which basically means you do A times B plus B times A. Or you might want to do what typically is called commutator, and you do A times B, and you weight it by -1. You weight it by the signature of the permutation. Now, of course, this can be extended for arbitrary arity operations by taking the coefficients of each of the terms being the signature of the permutation of the arguments, right? So that applies to n-ary operations. But in a sense, if one takes a deep look at what's going on here, this is kind of annoying that I have to change my thing for writing, but so if one looks deeply at what's going on here in the commutator case, you realize that for interesting algebraic phenomena like the Jacobi identity and so on, you exploit the fact that your bracket has a symmetry that basically values or weights the term with plus or minus one. And so you have to ask yourself, what is plus and minus one, right? It's really like going back to kindergarten and saying, the only weight I see here is a plus one. The weights that I see down here are plus one and minus one, right? So one has to think kind of deeply about what it means to be a plus one and a minus one in a ring of scalars. And what it means is, or the two aspects of it that I'm interested in this context, is on the one hand, you have a group, a multiplicative group, right? So you have a two-element group with multiplication, right? You have plus one times one is one, minus one times one is minus one, and minus one times minus one is one. So you have that particular relation, which of course connects with the permutation of two elements. That's just the permutation of two elements. But on the other hand, so that's the kind of multiplicative part. The additive part is that plus one plus minus one equals zero. So these form I'm going to call this property to be cancellative, right? Which or to be neutral, I think could also be called, right? So you're neutral when you add up to zero, right? And certainly these elements add up to zero. And of course, that's no mystery. Yeah, plus one minus one add up to zero. What's the fuss about it? Well, the fuss is that I'm going to abstract this property and say, I have my, in this case, let's say real numbers or complex numbers, or in fact, any ring where you have a unit. And this property basically tells you that you can find Z2, which is the group of two elements, embedded in your ring, or semi-ring actually, and that subset over there, so call it the Z2 in R, that thing is embedded as a multiplicative subgroup, but it is cancellative. So basically this adds up to zero, right? So this is an inclusion of groups, so I'm going to represent it by this. And actually, to make the plus more explicit, I'm going to call this sort of O plus like that. So when you add over the elements of the mapping, you get zero, right? So these are two properties. And so, okay, you say, right, let's see what we do when we have a ternary operation. So we keep that in mind. I'll leave it there on the screen over there. And now we go to a ternary operation. So I'm going to denote a ternary operation with just parentheses like this, ABC, right? And if you follow our streams, you're aware that there are many of these things that you can define with cubices. At some point, we'll show you some cool cubics graphics that for these products. But for today, just remember that you can define such things for cubic matrices. And so one can start to symmetrize, right? You can say, well, now I have 6 permutations in total possible, and you can start to weight your terms in the same way. So the trivial way to do this is to first just do all the permutations. Do ABC first, weight it by 1, maybe permute C and B like this, weighted by 1, maybe do a cyclic one, and so on, and just weight by 1. So this would be the analog of the first one up there, where I'm just weighting by plus 1. Now, I could also, as I said, anti-symmetrize with the permutation signature weight, which basically, as you know, will correspond to, in this case, a -1 here because I'm permuting C and B, a +1 here because this is a cyclic permutation, which corresponds to two transpositions, and so on. So this again relies on the +1 -1 elements. Now, in the ternary world, there's more, because you can say, well, I can actually permute. I can cycle my elements. With 2 elements, cycling and permuting is the same thing, but with 3 elements, cycling and transposing becomes a different thing, right? So you can do that, and so you for example can try to quote unquote anti-symmetrize, which I like to call it skew symmetrize, so that it's not anti, it doesn't imply that there is like a opposite or minus one kind of idea, by weighting your elements here, your terms, with a cubic root of unity. So this is CAB. So J here is a cubic root of unity. What property does the cubic root of unity have? Obviously that you cube it to the unit. That's, the fact that J cubed equals 1. And of course, it is a cancellative one, right? So, 1J and J squared, they form the cyclic group Z3, right? So that's what J cubed equals 1 means, that we have a copy of Z3, but it's cancellative because if you represent this in the complex plane, right, this is 1 plus J squared equal 0. The picture of this is very simple. You have something like this, right? You have 1, you have J, and you have J squared, right? And this is in the complex plane. This is 1, this is J, and this is J squared, right? You could do also the anti-symmetrization thing and add the negatives, and you would have something like this, adding all the negatives, which will be like a hexagon. You would have a hexagon of all these units, and it will still be. Now, in that case, you would have, I would write the same things over here, and I would say the relation is the same, but now instead of the Z3, I have a Z2 times a Z3 group, which means that you have 1 plus 1 minus 1 plus J minus J and plus J squared minus J squared, which corresponds to this hexagon. Again, multiplicatively, these are just roots of unit, so they multiply to form a cyclic group, and additively, they all lie on the unit circle, so they cancel to give 0. It's not a property of lying on the unit circle, it's a property of the exact distribution. They are evenly distributed on the unit circle. That's why they cancel to 0. All right, so then you might say, well, that's the end of the story, right? That's it. That's a ternary commutator, right? But no, because S3, the group of 3-element permutations, is not Z2 times Z3. It's actually Z2 semi-direct product Z3, right? It is not the direct product. It's not the Cartesian product, meaning that when you transpose 2 elements, you affect the cycle that you would perform afterwards, right? So it's, in particular, it's a non-abelian group. Z2 times Z3 is an abelian group. It's just the product of 2 abelian groups, and S3 is a non-abelian group. So if we were to have a full analog, and this is where the problem is headed. So presentation is over. The problem is that if one were to write this expression, you want 6 terms, 1 for each permutation, right? And I'm going to write it just with the coefficients, right? The first one is ABC, and plus some alpha, some value, times 1 permutation plus beta times some permutation plus gamma times some permutation plus delta times some permutation plus epsilon times some permutation. So that's 6 of them, right? So I have 6 terms, one per permutation of S3. And let me see if I can. So this is S3. And so the question is, can you find a set of elements, 1 alpha, beta, gamma, delta, epsilon, that have these 2 properties? They multiplicatively form a S3, so you would embed this into your ring of numbers, whatever your semi-ring of numbers, your field of numbers, whatever you want, your algebra of numbers. And on the other hand, you would have the additive S3 within R gives 0, right? Can you find this kind of situation? So the question is very concrete. If you give a candidate algebra, like the complex, like the quaternions, like the octonions, like the reals, the naturals, whatever, the question is, can you find 5 elements? 1 is the unit. We know 1 has to be the unit. Can you find 5 elements such that these 2 properties are true? And I'm going to refine this property slightly to distinguish it from the ones above. you want that all 6 elements are simultaneously cancellative, but no pairs and no trios of elements are cancellative, right? That is the constraint. So the constraint is that 1 plus alpha plus beta plus gamma plus delta plus epsilon equals 0, but no, for example, alpha plus beta plus gamma equals 0. So this is not allowed, right? You demand the top equation, but none of the bottom ones, right? So that's the problem. That's the open problem. This is the homework for the audience if they want to go and solve. Something that you need to know from the get-go is that because you want a multiplicative subgroup, you already know that the minimum situation that you're dealing with is that R is non-commutative. So your algebra, and I'm using these terms algebra, numbers, scalars kind of interchangeably because it is kind of weird what this needs to be or how to think about them. The stuff that, but I'm going to say it this way, the stuff that your matrices are made of, right? Like the scalars that you put into your expressions. And this actually calls back to, Dirac back in the day when Dirac was staring at the factorized Klein-Gordon equation and was thinking, wait, if those things were matrices instead of scalars, I actually would have the behavior that I want, right? I mean, this is kind of how historically it happened, right? Like he had this moment of, yeah, maybe I need to be a bit flexible. What I mean by, these symbols here that typically were just numbers, maybe if they are matrices, they do the work. So this is a similar situation here. So typically you would weight your expressions with numbers, quote unquote numbers. But if we want these properties to hold, we know these numbers are no longer multiply commutatively. That's what I would say, right? So that's the first thing, that these things are going to belong to some algebra that is non-commutative. Ideally, we want it to be associative so that we are not very far away from what we usually call numbers, right? So let's say that, and this is, by the way, this is R times. It's non-commutative, but let's say it's associative. And it's also unital because we have a 1, right? I mean, that we already have. And R plus is just a abelian group. The additive part, we're not changing. This is a abelian group. So yeah, that is the stated problem. That is an open problem, as far as I know today in algebra, whether you can find this. And so my potential answer to this, I was thinking about this problem, and my first potential answer was to think, okay, typically when one thinks about generalizations of the reals, right, of the fields of scalars that we typically use, one thinks of the division algebras, right? One thinks of quaternions, octonions, and so on. So I thought, yeah, there's something funny that happens in this construction because, you go real dimension, you always go even real dimension from the complex up, right? So you begin with real dimension 1, right? If you play this game of building the reals, you go the naturals first, then maybe the integers, maybe the rationals, then you go reals, and then you go complex, which is real dimension 2, and then you go quaternion, which is complex dimension 4, and then you go octonion, and you skip a few dimensions. But crucially, between two relatively highly studied fields, which are complex and quaternions, there's this real dimension 3 that is kind of skipped over, right? So I was thinking, hey, what if something, where are the number-like algebras in real dimension 3? And I mean, I was entertaining this idea just for kind of for fun, but then I came back to this question. I realized, wait a minute, 3D seems to be the minimal dimension that I can, at least intuitively imagine that this property can hold. Because if you think about this property in the plane, it is actually impossible, right? You can't have 6 linearly independent vectors that are going to be linearly independent in all subsets, right? That just cannot happen. So you can have 3 that are linearly independent and they don't cancel in pairs, right? But that's number 3. That's not the number that we want, right? Because number 3 is basically +1 of the dimension of your space. So in 3D, suddenly you open up more degrees of freedom, and there's a construction that you can make that geometrically will ensure this condition, right? And the construction is as follows. So you take um, you take a triangle, equilateral triangle, right? And you, which is very similar to the construction of the J's, so to speak, right? So this would be your sort of purported one, purported J, purported J squared kind of situation. And then but this is obviously at the origin. So what you do is you displace the origin. So basically you lift up this triangle by, let's say, a unit in the z-axis, and you displace it by, or maybe half a unit here, and half minus, sorry, minus half a unit over here. And so you get two triangles that are parallel, right? So I have this kind of configuration over here, right? With, two parallel triangles. And then what you do is you rotate by a sixth rotation. So now I'm kind of having a top-down view on the two triangles. They are overimposing. That's why I only see one. And then I rotate one by what is a sixth rotation? That's 60 degrees. Yeah, that's right, right? So you do this kind of thing, and then you see that you get this shape, right? With the triangle over here, right? So let me remove this thing. That is just the third dimension. So this is one. And now I'm going to give this different names, obviously. Now I'm going to call them, let's say, alpha, beta, gamma. And I'm actually, sorry, I'm going to call these two, I'm going to call alpha and beta. Because one we know it has to be one, the unit. And this we're going to call theta, omega, and rho, for example, right? So these are just names for the points in 3D, right? And so right now, because these two triangles are kind of a unit apart, you can see that if you draw your origin where it is in the middle, right, and you draw in perspective, you would realize that you have three vectors going up like that, and you have three vectors going down like that. They don't cancel. There are no parallel vectors, so there's no pairwise cancellation, right? It's clear from this top-down view that there are no parallel vectors. And then if you take any trios, right, they always kind of push away from the origin, right? So their sum is always going to be some non-zero vector sort of pushing away from the origin, right? So you have this condition that there's no trios, no pairs that cancel, but they cancel altogether because there are two triangles. The sum of these three is this vector over here. The sum of these three is this vector over here. They are exact opposites, and so they all cancel out, right? As three-dimensional vectors. So anyway, so that's where this shape comes from, right? So to make the problem a bit more, but this is beyond today's discussion. But the problem is now it seems that R3 supports such structure. You could find such three elements in R3 that satisfy that. Now the question is, what are all the possible non-commutative associative unital algebras in R3, right? That's just a very natural question to ask. And actually, you go to a paper, and I think, if I remember correctly, there's about 12 of these algebras, right? There are only 12 ways in which you can take trios of real numbers and multiply them together in a non-commutative associative unital way. And so the open question that I think is not so difficult to solve, but I don't have the right expertise to do, is does any of these algebras, these finitely many algebras that you can have in R3, satisfy the condition that these three vectors, which are three vectors in R3, right, are a multiplicative subgroup of the algebra, right? And in particular, they are a subgroup of S3. I mean, that's a bit more refined as a condition. But anyway, so that's the shape. And so connecting back what Nick was showing, so things up here, right? So this particular structure over here, that's exactly what you get when you look at, and the perspective here is a little bit difficult, but you know, in this triangle over here and this triangle over here are the triangles that I was, I mean, maybe I can be a little bit more. So that triangle is in the foreground. I'm going to draw with opacity here. This is the other, that's too dim. The other triangle is over here, right? So those two triangles are exactly the triangles in R3, right? In a three-dimensional vector space. Those are exactly the triangles that that I was identifying. And so the additional layer of coincidence here is that one seems to be able to do this kind of thing when taking 2x2 complex matrices. So you can have this kind of situation with 2x2 complex matrices. However, I think they actually cancel in trios. So it's a case where there are no pairwise cancellations. So for example, how does this fare over here, right? Like this is a case where you have 6 elements. They are multiplicatively a subgroup, and they all cancel out together. The problem is that they cancel in pairs and they cancel in trios. So it is possible to build a representation, basically a representation of S3 in 2x2 complex matrices and these are by the typical, Pauli matrices. It's a simple expression. You can
Pauli
represent.
matrices do this. I mean, it's simple enough to embed S3 in 2x2 matrices.
Let me see if I remember.
To real matrices, in fact. I mean, it's just an embedding of the dihedral 3 group.
So, all right. So let me see if I remember correctly. Basically, what you do is you take 3 matrices that essentially behave like the cubic root of unity. So identity, I think identity and I believe the 3 matrices were 3 matrices were identity, and then I think these matrices omega. I mean, I'm not going to use omega. I'm going to use J. I already used it. I think these were the matrices. Or maybe, yeah, not entirely sure, but basically this, and I think the others, you had something like maybe J squared.
I negative I like that, and then.
Oh yeah. Like this, right? Do you have the others?
I pasted it, but I can't edit anything. I don't know.
Oh, where is it?
Yeah, Dugan, if you want to maybe refresh, it might be that you don't have edit permissions. Yeah.
Oh yeah. Those are Pauli matrices. Yeah. But so they are not. I meant that they can be easily expanded with Pauli matrices, but they're not the Pauli matrices. There are 6 matrices. I believe they were times I. I think actually. Yeah, I think these 3. Yeah, I think that's right. So basically, you have these and the same ones times I believe. If I remember correctly. Anyway, the point is, I mean, we might want to do this explicitly in a second, but the point is that these 3 had the property actually. I was gonna make a fool of myself. So this is 0, 0, 1, 1, right? Sorry, that was pretty obviously wrong. So the point is that these 3 matrices add up to 0, right? And naturally, these three matrices add up to 0. And then when you multiply them, they multiply in a set 3 group. And then when you multiply with each other, they actually give you the set 2 semi-direct with set 3 in this case. So this is, this is S3. This is the right group. This is the group we want. The problem is
J a square root or a cube root?
It's the cubic root. That's the, yeah, sorry, my JSON.
So these are modifications of the Pauli matrices.
Yeah, you can think of it that way. So I believe this is true. You multiply J times J, is that true? This is going to be a very back to high school. Yeah, right, so J squared and here's J squared. So, right, so then I have to put the other one, and then if you multiply this by I imagine. Right, exactly, yeah. So, sorry, okay, I'll actually write the right matrices. And then this one actually gives you J cubed. All right, sorry, yes, okay, so, apologies. So this is the identity as we need. This is J, but this has to be identity times J squared, I think.
No, it's not 0.
No, it's not 0. So I think, yeah, but I think you have to mix with the others. Yeah. I should have brought I didn't think that we were gonna write the matrix explicitly. I should have brought the notes with the matrices. The point is, so frustrating. The point is, these three matrices, you're essentially representing a set 3 group within the 2x2 complex matrices, right? And each of them essentially, so multiplicatively they cycle through, and by conjugation you get the others. By component-wise conjugation of the matrices, you get the others, and they operate in such a way that they precisely give you set 2 semi-direct set 3. So it gives you the right answer. The only problem is that in trios they do add up to 0. So it's an improvement from the complex sixth roots of unity, right? It's an improvement from that, but it's not the full solution, because you don't have pairwise cancellations, but you do have three-way cancellations, and so anyway, that could be where the possible connection with the actual state space here happens, but yeah, maybe actually it makes sense to fully realize this. By the way, this could be Googled quite easily. Let me see if I can, because this is an S3 representation in. It's basically like a spin representation of S3. It's like S3 irreducible.
So I did Google. I found a set of not complex ones.
Of not complex?
Yeah. I found on Stack Exchange.
With the rotation matrices.
Oh, still 2 by 2, but
Yeah,
not complex.
yeah, 2 by 2 rotation, not complex over the real.
Real value.
Yeah.
And they implement S3.
Yeah.
Makes sense, right? Makes sense because those are that's the hydral group, right?
Mm-hmm.
But question is, do they have these properties?
So, which properties? The matrix he gave, where it's like,
So you have to add, do they add up to 0?
Seems like. Yeah.
That's
But
interesting.
that's I can post the link on Stack Exchange where I'm looking at.
Yeah.
I also put
yeah, it just looks like sine cosine of what you'd expect. Rotation matrix of pi over 3. 2 pi over 3.
right.
All right, here we go. This is what I meant. So those are the 6 matrices. I'm sorry. Those are the I'm going to copy them over. I was not so far off. Just from pure memory.
No, it's a complex representation. Yeah.
Yeah. I'm sorry. Yeah. Oops. How can I edit?
Oh damn. Pardon me. Did you lose edit privileges? No.
Oh, no. Okay.
No.
Nick can do
For some reason, I can't.
Oh, right. So actually, yes. So sorry. Yes, it was kind of trivial. What you do is identity and then diagonals with a conjugation happening in alternation, right? So in those three, you can clearly see that they cancel out. They all cancel out, and they don't cancel in pairs. That's where this cool trick, quote unquote trick, of having them diagonal but not with the same elements, basically permuting their entries. But they do add up to 0 in a trio, right? Like you can tell that component wise, it's always the same sum. It's always 1 plus j plus j squared, right?
Mm-hmm.
So yeah. So did you post the other one? Let's see. Where's the real representation?
They're just to the right of Pauli matrices.
Oh yeah. Oh, sorry. Let's see. The stars. Interesting. So they cancel EDB. That's non-zero. EDF. That's non-zero. EAF. Okay. Now, do they cancel in pairs?
That's where writing code is much more faster than that. It's like rotation matrix E over 3.
Yeah. Do you check?
Well, I'm gonna check now.
Okay.
And
Interesting. Huh, this is very interesting.
is there an easy way to generate all of them as a group data? Metric free.
Right, so
Metrics.
interesting. Huh. This is very interesting. Yeah, they clearly don't cancel in pairs. I can see that. I also think they don't cancel in trios, right? If we can get computational confirmation, that'd be great. Did you, Dugan, by the way, did you think of this because of the property that I was mentioning, or did you just remember that there's a real representation of the dihedral group?
I mean, the dihedral group is the symmetry is on a triangle in the
Sure.
plane. So if you just think about, rotating by 2 pi over 3,
Yeah,
and
yeah.
then, and then composing with the reflection, then those
Right.
are those are operations of the plane that can be modeled as
Right.
planar symmetry.
Yeah, yeah, yeah. Okay, right. So
So C is a reflection, right?
C is a reflection, yeah.
Mm-hmm.
The rotation is the which one? They all have to be
They are all
they're all with reflection, right? Essentially. There's no pure rotation.
no. I don't think there's pure rotation. That makes it very interesting.
No, the D is a
Maybe
pure
part minus.
rotation.
It's a minus.
D is rotation matrix 2 pi over 3. F is probably twice that. Yeah.
Okay.
And then A and B are the reflected.
Yeah, yeah, yeah. Right, right. Were you checking that, Nick, or should I do it myself? Like,
I'm just trying to figure out how to write them in terms of rotation. It's just weird to type them out by hand.
What?
I understand.
I could have done it already. I don't know.
Just use
Some reason.
rotation matrix. I don't understand. Here, I'll post what I have.
Oh, there's not
Yeah, those
quite.
those are clearly rotation values, right? Like 1 minus 1 half minus 1 half. That's the
But just the signs are weird.
signs are weird. Okay, well, it is what it is. I guess it's the kind of the philosophy here. It's funny. I mean, by inspection, I think it's very clear that they are not canceling because they would have to cancel component wise, and well, wait. No, the EDF cancel out, right? Let's see. 1 minus 1. 0 plus 0. 0 plus 0. 1 minus 1. Ah, unfortunate. No, they do cancel interiors. Sorry. Yes. So no good, unfortunately. Yeah, I was getting very confused with science because of the radical symbol. Just was making me visually see some of the radicals as negatives. But but they clearly, so EDF cancel in a trio, and I assume CAB cancel in a trio. Let's see. -1 + 1, 0 + 0, 0 + 0. Sorry, 0 + 0, yes, and +1 - 1. Yeah. EDF cancel in a trio, CAB cancel in a trio. And like in the other case, they don't cancel in pairs at all. So I think this is just the same situation. It's just a 4-dimensional. Aha, right. So, okay, so here's the geometry, right, that I was mentioning last time, Nick. So what is going on here in 4D, right, is that we have basically a plane, and then basically an orthogonal plane that has no intersection, right? Because that's possible in four dimensions, right?
Okay.
I mean, it has intersection at the origin, but you know what I mean, right?
Yeah.
Yeah.
So this is are people following that thing? In 4D, you can have two planes orthogonally, not intersecting, right? That's we have to honor our title of the live stream. This is the higher dimensional part, right? And so what's happening in that domain is basically that you have a Z3 diagram over here, and you have a Z3 diagram over there, right? So let's try and do something a bit more fancy. So you have like blue over here, and this is an R2, and you have red over here, and this is an R2, and these two are orthogonal, right? So they do add up to 0, but they are actually two copies, as is kind of obvious, right, from the construction. In the complex case, at least, it's very obvious because this construction here is clearly placing the j's in the right positions. It's all made of 1s and j's, right? I mean, j's and j's squared, right? So basically, you're improving from this situation by essentially copying two planes and putting them orthogonal to each other in 4D, right? Because there's free real estate in 4 dimensions, right? And you say, okay, I can do this. I have two planes, I just put them orthogonally to each other. But so the mystery, this to me like further constrains the exercise. This makes this question even better in some sense mathematically, because it tells you that you have the solution for the set 3 group, the cyclic 3 group, and you say, okay, take that, go into 4 dimensions and just orthogonally put them together. And there you can use your algebra of matrix multiplication to do multiplication, and it works. But you kind of overshoot because you are in 4 dimensions and you are 3-way cancellative. So it's kind of a motivation to say, actually, come down one real dimension, and actually try to pack the algebra in this odd number of dimensions that the usual extension kind of field extension game doesn't naturally account for, and or I guess the division algebra game is the extension field does. But yeah, anyway, so this is the thing. This is the geometry of it. Sorry that was slow to realize that we actually needed all the explicit messages, because we definitely did, to see this pattern. Another question is, from the quantum point of view, what, like, your understanding, Nick, of qubits and so on, as you've been studying them, like what comes out to you when you see the irreducible representation of the dihedral group, the S3, with complex matrices, like this, like these, right?
Well, it looks like some kind of projection. It's like now in that recent free blue one brown, right? Projection of the hypercube from 4D to 3D across this diagonal, right? It kind of makes this shape. Here it's you basically make this star shape by projecting some four-dimensional shape to, right? Maybe but that's maybe a bad intuition.
Projecting.
Yeah.
That'll be interesting. Yeah, so like casting a shadow, right, kind of thing.
Yeah, across the special dimension, special
Some
axis.
direction, right? Some particular direction.
Yeah, James is.
Oh, you mean the that one? Yeah, I watched that video. That's cool.
He had this rhombohedron or something like that shape that you get when you project this hypercube to the 3D, and you get the same kind of shape for the qubit if you essentially make those two dual tetrahedrons and well, at least in the cube you kind of extend some of the faces and make a convex hole or something like that. You can make the same kind of shape. This is kind of yeah. Let me put one.
Would be interesting because
Two tetrahedrons, don't they make a cube in opposition?
Yeah. So there's something more in the qubit representation than in the thing that I'm pointing at, because my thing is a kind of six-pointed star, and the two tetrahedra is an 8-pointed star, right?
Yeah.
So there's something more, but what I feel is that my intuition tells me that those tetrahedra, right, they're actually made of 4 families of these 2 triangles, right? Like you take these 2 triangles, right, and you can look at any pair of parallel faces of the tetrahedra, right, and they are in that configuration, right? So in the same way that you say
none of the faces are parallel.
No, they are.
Which one? Where?
With of opposing.
Oh, you're right.
From one to the other, right? From
yes.
Like one face from each tetrahedron. I mean, right?
Mm-hmm.
They are parallel 2 to 2, right? Or 1 to 1. Sorry. So what I'm saying is, the same way that you can perceive the 2 tetrahedra as implying a cube, right? You can also see 2 tetrahedra as just 4 instances of these 2 triangles, right?
Mm-hmm.
So that number 4 is suggestive, right? I feel like that number 4 is quite suggestive, right? Like, it seems like it could be something like the 4 projections of something, right, onto 3D. This is kind of the numerological guesswork that I imagined that was going to happen. Sorry, say it again.
What are we projecting to 3D?
No, I'm just using like evocative thought here. I'm not arguing mathematically. I'm just saying that. I mean, I'm doing more than pure numerology, because Nick just mentioned something quite interesting. That what is in my mind is that clearly, this shape, the 6 vectors in this configuration I want, clearly can can be imagined as a 3D projection of this 4D shape, right? Like remember, this thing over here lives in an ambient kind of with a corner like that of R4, right? So if you cast a shadow from R4 down to some R3 in, within this space, if you do it properly and you don't degenerate some of the vectors, you're going to get basically something like that, right? I mean, you're going to get the same shape, but just one dimension lower, right? That's usually what happens with projections when you don't degenerate, right? Like the shadow of this.
Let's say it again.
Yeah. So if you cast the shadow of a 3D object, right? You're going to get, in terms of kind of linear independence of the elements, right? Like you're going to get the same number of objects unless you degenerate in some orthogonal direction, right? So my point is that if you have in 4D, you have this particular representation, let's say with the real matrices, right? Like this exact thing. That's what it looks like. These are three. I mean, we could even check that, I mean, it's easy to see, like E times C dot product, right? You take the 4D dot product of matrices. You know what I mean?
Yeah.
Would you-
You do a projection matrix.
4D, treat the matrix as a vector and just take the dot product, right? So component-wise multiplication and then add them together, right? It's obvious to see that E times C is 0, right?
Oh, component-wise, yes.
No, you know what I mean? I'm taking the matrices as vectors, right? In R4, right? And
Right.
I'm taking their dot product in R4.
I see.
So
yeah, that's essentially like what in Hilbert space you do when you project your 2x2 unitary matrix or 2x2 density matrix to a phase space presentation. So you have a Hilbert-Schmidt product, which is just a product of matrices and a trace, right? But in that, when you do it in vectorized form in 4D, it's just dot product.
it's just dot product, exactly. Yeah. So here is actually literal dot product of the components, right? In the real case. So as you can see, E and C are orthogonal, and I would suspect that therefore D and A would be orthogonal. And you can check, right? Like you do component by component, 1 minus square root gives plus square root, the other gives minus square root, and the other gives minus 1 plus 1. So everything cancels, right? So they are orthogonal. In the two trios are cancellative and mutually orthogonal, right? So that's why the picture above is not just a cartoon. It's actually what's going on, right? Geometrically. Like this red and blue picture is what is going on, right? So what I'm saying is that if you're in that 4D, right, and you project down to a 3D, so take any three-dimensional subspace through the origin and project onto it, unless you happen to align one of your 6 vectors in the unique orthogonal direction of that plane, the kind of object you're getting in your R3 is exactly 6 vectors, right?
Right.
I mean, what I mean is 6 non-zero vectors, right? Some of them might be 0 if you align things badly, so to speak, but generically you would get 6 vectors down in R3. So my point is that maybe a way to get a solution for the problem is to somehow project the 4-dimensional thing into R3 in a way that you can preserve matrix multiplication somehow, that you have a projected multiplication still operating. But anyway, that was just the comment here with what you said, Nick. But the evocation that I'm giving you here is that this double tetrahedron thing that you showed for the qubits, sure, you can see 2 tetrahedra because that's how we think. We see the kind of compact shape as the more unique thing, but just as well, you can see this as a collection of 4 parallel triangles, pairs of parallel triangles, right? And so
Yeah. It's like you're dropping away some of the dimension. In this case, it's natural to drop away the identity, right? You have identity plus 3 Pauli matrices, and you kind of ignore the identity one you project along that dimension. That's why
Right.
you kind of squish your tetrahedron into a triangle.
right, right, and the thing is, you can do this in 4 different directions, right?
But
Right.
but identity is exactly like a diagonal. It's like you don't singling out one of those 4. It's like 1, 1, 1 vector in 4 dimensions.
Really?
Yeah. Well, this intuition comes from the probability intuition, because it goes directly through the center. That's 1, 1, 1. It's a uniform distribution essentially, right? And that's yeah. You can make this analogy more rigorously, but I don't know how.
Yeah, sorry, I'm listening. I was just not here. Right. So, okay, maybe my numerology is misguided. Just thinking that that 3D object seems to have 4 non-orthogonal, non-3D orthogonal, but 4 instances of. I mean, to me, that's just kind of. I mean, I don't know. At this point, I'm just speedballing about kind of what a tetrahedron feels like in 3D, right? But like the fact that you have 4 faces is like you tried to be orthogonal in 4 dimensions, but you failed, right? Like
Well,
you
we can try to make like a one-dimension-less analogies. Because
yeah,
I
that
was
might be useful actually. Yes, that's a good
I
idea.
have this. Let me find some picture.
Do you want to share, or should I keep
I was
sharing
just
on that?
gonna paste some picture there.
All right.
Because I was calling this like this 3D analogy for the qubit, because qubit is essentially like a 4 dimensions, right? Geometrically, with those tetrahedrons and all that. But you can go 1 dimension lower. It's not a sensible quantum system, but you can start to think of them geometrically anyway.
You do it by somehow restricting, or just by analogy.
By analogy, it's just like what is the analogous simplex in 3D? Like what is the block sphere? Like this is like the triangle. See, this is like analogous of a tetrahedron, and the block sphere, 1 dimension lower, so it's like below qubit.
Huh,
You know,
that's fun. That's interesting.
and you can imagine what the projections are. It's like here it's a 3-dimensional simplex, and how do you project it to 2D? You have to project along this diagonal, or you do some kind of rotation and drop one of them, right? And that's essentially what you do in order to project phase space in 4-dimensional to the sphere and the tetrahedron. So those shapes are analogous.
You mean the diagonal of the cube?
Yeah, the diagonal. It just goes through this center of the simplex and the circle, and 1 dimension higher is going to be center of the 3-dimensional simplex or block sphere. So those are the analogies. So that's why I said that you kind of dropping when you do this projection, you drop this dimension along this diagonal. You
But then
project
wait,
different.
but then right, huh? But then it's exactly what I was saying, right? Because you have well, many diagonals? 4 diagonals in a cube.
Yeah, one for each vertex along a face. Wait a minute, no, there are 6.
No. I mean, there are only 2 diagonals, right?
On a
Crazy?
cube?
No, there are 4 diagonals, right? I'm not going crazy.
Yes.
Like,
there's 4 diagonals.
actual diagonals, right? Like bulk diagonals.
Yeah.
There are
4
4 of them, right?
Mhm.
Right. Is this also true for a hypercube? Doesn't sound right.
How many diagonals? So if there are in a cube there are 8 vertices, and each diagonal is sort of like going through 2 vertices that are opposite the origin from each other. So in 4 dimensions there are how many? 16 vertices, 8 diagonal.
Right.
And so you can look
eight
at
diagonals.
what the symmetry group on a cube does to the 4
Right.
diagonals.
So
you have like an actual.
8 diagonals. Right. So 8 diagonals would be 8 triangles, right?
No, 8 line segments.
No, I know, but with a qubit projection, Nick. I mean, what Nick was saying. One triangle per diagonal, right?
Yeah, but
Well-
Nick's not projecting the hypercube; he's projecting a simplex.
Yeah.
No, I understand.
If you want to project the cube itself,
No, I was just thinking, but I guess 1 dimension higher, so it doesn't work. Because if you do, right?
Yeah, so I mean that's the question. Okay, like what shape do you get if you project the hypercube along a body diagonal to 3 dimensions, and you take the convex hull of that? Because if you take a 3-dimensional cube and you project it along the body diagonal, you get a hexagon. Where if you project it along a face first projection, then you get a square.
basically shape-wise, there's no, it's like in the 3D to 2D projection analogy, if you project a cube, you get either a hexagon, right? Or a cube. If you project it along the diagonal, always.
Along a diagonal, you take a cube and you turn it, and you project along the diagonal, and the shadow will be a square. I'm sorry, a hexagon.
Yeah,
Yeah.
that's right. And Nick, by the way, what if you draw? Can you do the graphics? I guess that's just a graphics object, right? Would you render there? The q root 3 it
It's a qubit when p is square to 3, right?
It's a qubit or something.
It's like a scutrit. I don't know. I don't know how to call it.
I guess the Greeks were not, they were quick to give names to the, when they did like semi for half and things like that. They also did sesqui, which is 1.5, right? But they were not keen on doing square root of 3.
Yeah.
They might have had a metaphysical reasons not to do that. So anyway, can you render the three? Can you add the triangle that is parallel? So basically, on the other 6 vertices. You know what I mean?
Parallel to what?
So
to
if you just draw a triangle between the other three non-diagonal vertices of the cube, right?
the three non-diagonal. I see.
Yeah. So right now you know what I mean? Like there are three vertices
Hey.
being, yeah.
Yeah. So, well, this particular one is I made with some implicit region nonsense. Hold on.
Okay. I mean,
Oh yeah.
I might actually just.
The simplex, another one.
I'm gonna make this my own notebook as well because I think. Just as a graphics object.
Okay, I'm gonna paste whatever I have.
Yeah.
Something like this.
Yeah. That's the pair of triangles, I think.
Sure. Why wouldn't
I mean, what I mean is that is my pair of triangles I'm trying to find, right? I mean, this is just me learning geometry as we go. Like, I actually did not know that that those pair of triangles actually happen to be the kind of diagonal transversal triangles of a cube. That's an interesting fact. I don't know what to do with that fact, but it's certainly a fact. Okay, interesting.
Oh yeah, that exactly shows that projection and ignoring those diagonal vertices, two diagonal vertices, that those two triangles touch.
It is, yeah.
You kind of ignore them. They all go to the center.
That's cool. And that's why it's also an easy way to see that it's an easy way to see that all the points of the triangle actually lie on a unit sphere, right? Well, unit if you choose the right radius, but on a sphere, right? Because they all the vertices lie on a cube, and you can describe a cube in a sphere, right?
Yeah.
That's right.
Sure. Yeah. Right.
Yeah. So it's right.
Yeah.
I mean, just an interesting. I mean, I'm saying sphere here because sphere, it's kind of the analog of what I was describing here for the J cubed thing, the cubic root of unity thing, right? That you have the circle in the complex numbers as this U1 thing, right? This very special object that we use for a lot of things. Algebraically is like, its angle basically is the thing, right? It's doing 2D rotations. Here, there seems to be something that is a sphere, that is going to be some kind of unit sphere that algebraically might encode something interesting, important, whatever. And units scattered around it behave like units, are unit-like in some sense, right? But the real question is, I mean, the real mystery for me here is, what is the algebra that I put around this thing in 3D to make it into something like a number, right? That I can. It's basically making space into an algebra. That's a very kind of simple way to put to our audience as well. If anyone is following at this point, which I think we lost most everyone, but it is kind of Maxwell's dream. Like this is sorry, not Maxwell's, Hamilton's dream, right?
Mm-hmm.
Of like trying to find the 3-space algebra, just like the complex numbers, right? I mean, inadvertently, they discovered quaternions that way, right? But their goal actually was to use 3D as an algebra proper, right?
Mm-hmm.
and they couldn't escape the fact that they needed to throw like the scalar in the sort of with the ijk, to make everything work. So the mystery remains, almost 200 years later. It's like we want to see if there's a way to make space into an algebra in which it can act on itself. And I think all these matrices are very interesting because, of course, SO3 happens to be, SU2 double cover of SO3, and SO3 happens to be three-dimensional. So near the identity, SO3 looks like R3. So SO3 gives you a way of, so SO3, by the way, these are 3D rotations, right? This is just, they act on themselves, right? You can multiply them together. So if you look at the rotations close to the identity, that chunk of space looks like a volume, and that volume has an algebraic structure, right? Which is SO3.
That volume is enclosed under the operation, though, right?
It is not. It is not. Not there. But under there are some neighborhoods where you can see, like, I mean, not a closed. You never get a closed operation. That's the point, right? I mean, you only get a closed operation in the whole of SO3, and that's not R3, right? It has some more interesting topology than that. But yeah, anyway, it's interesting because right. I mean, the reason why I was thinking that there might be a connection with quantum stuff is that I think your idea is very good. Like, if you somehow project down, like, it seems like the quantum story is kind of four-dimensional here, in a sense. And it might be that the three-dimensional story is a projection of that four-dimensional story. So maybe the problem can be somehow simplified by saying, can you find a projection of matrix multiplication? So basically, actually, this multiplications. Oh, wow. I just saw.
Getting deeper. Yeah, it's the turtles there.
That's the limit of the dimensionality. But
You find the dimensionality tortoise. Okay, so like, even with these matrices, right? This is an exact four-dimensional algebra, right? In fact, is that algebra? No, this algebra is non-commutative, right? So it can be, but is it? Nah, whatever. I don't think it's the quaternions, right? We might not be like fooling ourselves here. It shouldn't be,
What
right?
would you say?
No, it's not, right? Like,
Quaternions?
2 by 2 complex matrices as an algebra, as a four-dimensional real algebra. It's not the quaternions, right? Or is it?
No. The matrix group is 8-dimensional, 8 real dimensional, right? If you want to.
Oh, sorry. No. Okay, sorry. No.
I mean, it is something to think about. Can you embed like S3 inside of H?
Yeah. No. I actually meant.
Quaternion.
I didn't mean. Sorry. I said complex matrices. I meant SU2. Well, SU2 is not but SU2, the Lie algebra. SU2, the Lie algebra, is it the quaternions? No, it shouldn't be, right? Like, matrix representation. Uh, 2 by 2 complex matrices. There are injective homomorphisms from quaternions to matrix rings. This injection.
It's also like some kind of Clifford algebra. 1-1 Clifford has the same matrix representation. Yeah. 2x2 complex one.
Interesting. Right. So anyway, but the question remains. What I was going to say is, you have this algebra of SU2, whichever representation you like, and then you take some projection down one dimension, right? So you choose a three-dimensional subspace within, which is like to say you choose three matrices, right? Or one matrix, and you basically project down to the orthogonal complement of that matrix, right? So that would be the question. Can you find one matrix in SU2 so that the orthogonal complement retains an associative algebra structure? I think that's the question. But what does that mean? Does it mean that you want to find... Wait. I'm very confused for one moment. Just reality check. The polymatrices are the Lie algebra, right? I'm not going crazy. Polymatrices is
Hermitian, because they're Hermitian, right?
Right. It's small SU2, right? Not big SU2. Small. Okay,
Right.
yeah. Sure. Okay, yeah. Just reality check. All right. So then maybe the question is, can you find... but wait. This is interesting. Okay, so it might be more interesting as a question. So SU2 as a Lie algebra, as an algebra of matrices, is an algebra under the commutator bracket, right? That's you take any linear combination of polymatrices, you get back a linear combination of polymatrices when you take the commutator of those, right? But the product, the matrix product, the associative product, does not close as SU2, right? Generally. Like you take two polymatrices, you multiply them together, you don't get a polymatrix or linear combination of polymatrices, right?
No. You got another polymatrix.
I thought the point is that they did form a group.
No.
They're
Maybe
both
I'm
group in the algebra, I think.
Okay, yeah. So sure, yeah. Like, okay, this particular case you do get, but actually, no, don't you get some signs?
Well, if you close it with the signs, then maybe. It's like a Pauli group, essentially what it is. It's like x minus x, y minus y, z minus y. 1 and minus 1.
Yeah. So, but anyway, the point is that a general linear combination is not going to close under matrix multiplication. It's going to close under commutator, right?
Okay. Yeah.
That's clear because that's what it means to be a Lie algebra, right?
Yeah.
So the question becomes more interesting because you can just ask, can you find three-dimensional associative subalgebras of SU2, right? Or let's say the matrix representation of SU2, right? The faithful matrix representation of SU2. Like that's a meaningful question. It is not trivial because actually that question can be asked here all the same, because wait, Nick, couldn't it be that you were confused about signs here? Didn't you say that the signs were weird here?
Well, I think Dugan reproduced it anyway. So now I was trying to make it work with the pi over 3 rotation, something like that. I don't know.
So, all right. So no, oh, that's funny. Okay, so that's actually the representation of the group there. Yeah, but anyway, the representation of the group here are not the Pauli matrices. That's important. So they are these matrices, right? So I guess that could be the question if you can find a associative subalgebra. I mean, forget about the dimension for now. But if you can find an associative subalgebra of those matrices, maybe magically the subalgebra is three-dimensional already when you find it. And then you don't have to project in some sense. I mean, you can project if you want, I guess. But if you find a subalgebra, that could be your thing. That could be your the instance of what you want, because you have a three-dimensional thing, assuming it's codimension 1, right? You find a subalgebra of things that are
So the
close
Pauli
to
matrices generate an algebra that's 16 elements.
of 16 elements. 16 is what? 4 to the power of 2?
Mm-hmm.
Yeah, makes sense, right? Because
It didn't make sense to me. I guess like
no,
just
wait,
looking at the Pauli matrices, it's not obvious.
wait. They
Well,
have to.
it's that sign, right? It's like every Pauli matrix comes with a plus minus sign, so 2 to the 4.
Mm-hmm.
Right, sure, yeah. Yeah, in that case, yes. Okay. All right. Anyway, so that's kind of a question thrown out there. We can relay it back in the Discord server later on if people want to follow up on it. But I think that's the closest link that I can find after today's discussion, is to think about the fact that your Hermitian matrices represent, these are, if I understand correctly, these are qubits, right?
What exactly is the cubic?
Hermitian matrices. Well, no.
What in what sense?
They are no, they are Hermitian matrices with trace 1 are density
One.
matrices, right?
Yeah.
Okay. Wait. Right. Trace 1. That's a subspace. That's a three-dimensional subspace, right?
Yeah.
Wouldn't it be fascinating? Wouldn't it be fascinating is if qubits make these elements? I mean,
How do we
can you
make
multiply okay, random question that's detached from this. Forget that we're talking about this for kind of refresh your minds. Can you multiply 2 qubits in any meaningful way together to give another qubit uniquely? Two of the same qubits, I mean, of 2 possible quantum states.
Not the tensor product.
No. Two
Yeah.
of the same. Imagine you have 2 virtual ones and you're saying, what does it mean to do one times the other? Does that make any sense?
WKK made a comment in the chat.
Yeah? Let me see.
I'm not sure if he was responding to you or responding to me. He says, okay, maybe it was a different response. He says, if we count the pair for 1 as well as 3 times 2, but that was in response to a question of, does this other thing have 6 roots? So, sorry, yeah.
All right, yeah.
Unrelated.
I guess I'm still sharing this. Yeah. So does anyone have any thoughts on whether we can multiply two qubits together? Like, and this is related to the question I asked the other time, right? Like they are density matrices, so you can multiply the matrices together. And is it true
So
that
you can do something like weird. Like, for example, you can treat one of the qubit as a density matrix, which is a Hermitian thing. If you treat
Yes.
it as a Hamiltonian and evolve your other qubit with that Hamiltonian to get another one. So basically exponentiate one of the qubits, and then
For how
it's
long?
like
Evolve it
no,
for how
just
long?
no, you basically make an exponential map from one of the qubits, and then act with that thing on another
Oh,
one.
like unit time evolution, something like
Yeah, yeah, yeah.
that. Huh. Yeah, that's a possibility. I guess the other question is, it's not true that trace.
It's just not gonna be like traceless. You know,
Unit trace though, right?
yeah.
Has to be unit trace, not traceless, right?
Well, the density matrix itself is unit trace, but the Hamiltonian
Ah,
should be traceless,
wait, what?
right? Or
No,
as a
no.
as a Pauli matrix itself.
Is it traceless?
It's one of the bases. You can decompose it in a way, do some kind of Pauli decomposition.
But the Pauli matrices are not traceless. I mean, okay, the Pauli matrices are, but the basis matrices are not, right? Wait.
Well,
No, yeah, yeah.
just the identity is it's like you have the identity and the free Pauli matrices, those traceless ones, free traceless ones, right?
Yes, yes. Yeah, no, but the SU2 algebra is the three Pauli matrices. It's not the identity.
Yeah,
Yeah.
that's why it's like you have
Yeah,
to
yeah,
get
yeah.
rid of identity first in order to make a traceless one, so that it looks like a Hamiltonian, and you can evolve it.
Okay. You can evolve it. Interesting. So, I mean, this is related to what I said last time. Like, how do you interpret density matrix times a density matrix of the same density matrix of the same kind multiplied together?
It's well, yeah. It's geometrically, it means essentially, I think, when you get rid of those identity, because you have a block vector, you kind of can turn it into rotation, right? You make a correspondence with some Euler rotation angles and all that, and that's how you do the rotation.
But right. Okay. And then, so trace. It's not true that unit trace is preserved under multiplication, right? It's like obviously not true, I think, right?
Unit trace.
Unit trace.
Like you get one out of the trace. I mean, that's never possible here. That never happens here. Right?
No. What I mean is, for density matrices of quantum states, right? One of the requirements to be a density matrix is that you have trace one. Like your diagonals sum up to one, right?
Mm-hmm.
And it is not true that if trace of A is one and trace of B is one, that trace of AB is one. I don't think that's generally true. Nick, I think you dropped out. I don't know if you heard my question.
Yeah, I drew that. What was the question?
I mean, it's kind of a more like a statement that is kind of obvious that trace one matrices don't close under multiplication.
Should be. Yeah.
Right.
It's just from the properties of trace. I think.
Wait, it's true? No. Is it?
Well, trace of the multiplication is. Oh, hold on.
No.
Yeah.
I think it distributes like that.
No. Trace of the multiplication is only sees the pair, not the order, but it's not like the multiplication of the traces or anything like that.
Yeah. That's.
I mean, it's obvious with diagonal matrices. You just take two diagonal matrices, multiply them together.
Yeah.
It's obvious that they don't. So
Yeah. It's not.
right. So okay, then the question maybe, can be formulated in this level of generality. Can you define an associative product of qubits? It's like maybe I'm going all the way down to this level of simplicity of question. It's like, can you, just for sport, can you define an associative, unital, non-commutative associative multiplication of qubits that is not the tensor product? Because that just takes you out of your space. It's an internal operation. It will be crazy. Like I would just, call quits if this happens to be the solution to the ternary commutator thing. I'll just quit. Like the level of cosmic joke, it will be too much. I don't think it's going to be the case. So that's why I'm safe to say I would quit if it happens.
Yeah. Well, I have a Heisenberg picture. You can turn every pure state into observable, right?
Yeah.
Because you have a vector and you can turn it into an axis. That's the measurement, projective measurement that you're doing.
Yeah.
You can think of each qubit then as observable, which you can multiply together, to make new observables. So.
Wait, how?
Maybe that way. Well, just physically, it's just.
Yeah, but the problem is that didn't we agree that the observables are not the same thing as the states, right? And that's the problem.
They kind of not, but you can squint.
Sure.
You have Schrödinger Heisenberg, duality. You can kind of
I think that's there's something like at this level of inquiry, like we need to actually be careful with those things because if we knew that the unit trace matrices close under multiplication, this will be a possible solution. And if you forget about, because is it true that zero trace is preserved under multiplication, right? Vanishing trace is preserved under multiplication. Maybe not. Is it?
Well, usually maybe.
I don't think in general, because same argument applies. No, it's not. Because you take diagonal matrices and you clearly do not get that result. Because it's not true that, that result will be true in a world where you can factorize things. A times B plus B times C equals A plus B times B plus C, right? Sorry, A plus C times B plus D. You know what I mean? Like for that to be true, this would have to be true, right? Like so A B plus CD would have to be equal to A plus C times. So for some bright high school student somewhere, they live in a universe like that. But unfortunately, most of us don't live in that universe. Yeah. No. I don't know. Maybe
Well,
that's an additional axiom for your ring of scalars. You know, they have to be associative, non-commutative, and then also that this weird distributivity, semi-distributivity kind of thing. In which case, I guess your traces are, if this is true, I think your traces are preserved under matrix multiplication. I think that's sufficient for that in general. So when they are zero, they're yeah. But anyway.
Yeah, we've got 5 minutes here. I don't know if you want to wrap up for this stream.
Yeah,
I
let's
mean,
wrap up.
the
Yeah.
fourth dimension is time, and it's encroaching upon us. We have a possibility exclusion principle where I can't be in two places at once.
Yeah, for sure. Anyway, thanks for the session, guys. I appreciate it, the insights. So my wrap up is we delved into this geometric structure. There clearly seems to be some very strong parallels. We did make some progress. I'm surprised that we actually I know a bit more now than I did a couple hours ago. So yeah, the summary is it's the same as in the start, right? Like there are these two completely unrelated worlds. One about qubits and quantum mechanics and kind of geometric representations of quantum physics. The other, this completely separate world of ternary Lie algebras and how to generalize the commutator. And there seems to be a particular 3D geometric structure that is very closely related to looking at a cube in the right way, basically. That seems to be completely common in both. Like they show up in completely different sense, a completely different perspective in each, and playing completely different roles. But they both, understanding that structure seems to be crucial for some of the internal understanding there, or like some of the internal sort of operation of that realm. But the mystery remains. You know, if anyone in the community wants to pick up the problem, this could be a cool sort of affiliate research kind of thing that we can explore. And actually, it will have to be done computationally. So it's good that we have our technology stack, because we can just enumerate all the algebras at the right dimension and then do the brute force search for the matches.
I think we should list that as a hackable project. Potentially, if we can just do like a small little write-up on it, 1 or 2 paragraphs, link it to this video, then have it as an open challenge for someone. Yeah.
Makes
Sounds
sense.
good. Okay, great. Thanks for the session
Right.
today, guys. That was fun.
Thank you very much. Thanks.